Isomers means that they have the same molecular formula, but different structural formula, right? So when it's same molecular formula, different structural formula, actually we call them structural or constitutional isomers, okay? So this part, we actually give you, we can categorize them into 3 different types of constitutional isomers. We acronym them by CPF, okay? C stands for chain. So I'll give you now some example of chain isomers, which means that in this case, whether you're branch or unbranched. So one good example will be actually your C5H12, okay? There's none other than your pentane. I'm going to use line structures. So you have a straight chain, okay? Or I can start branching them into this. So basically in this case, the relationship between this and this, we can call them as constitutional isomers. If I want to be very specific, then I'll say that between this and this, the relationships is they are actually chain they display chain isomerism, all right? Or they are actually chain isomers. Can? Okay. So if not, I move to the next one. Next one we'll be looking at is actually your P. P is actually your positional isomers. Positional isomers means your functional group can actually shift, all right? So a good example is your C4H8. C4H8 is none other than actually has a double bond inside, all right? So in this case, we have a butene, and you probably know that you can have Bu1 in or Bu2 in, right? So it's 4 carbons. So the double bond can be between the first and second carbon, or the double bond can be between the second and third carbon. So the relationship between these 2 isomers, we can call them as constitutional or structural isomers because their structures are different. At the same time, you can see that their functional groups is actually a different position. So we can call them position isomers as well. Last one is none other than your functional group isomers. Okay, functional group isomers total, there are actually 4 sets that you need to know. All right, so it's going to be a bit crowded here. So let me explain. The first set that you have to pick it up, which actually, if you have done it in actually your O level, you will learn that it's actually your carboxylic acid and ester. Okay, so I start with carboxylic acid and ester. So again, I'm going to use line structures. Let me give a quick example. So this will be, say, for example, our carboxylic acid structure. This will be none other than our propanoic acid. All right. So propanoic acid, the molecular formula would actually be C3H6O2. Okay. Obviously, this C double bond O COO, we can actually shift it in to create an ester. So let me show you how this is done. So in this case, this will now be an ester. Okay. What is unique about these functional group isomers is that not only will their physical properties differ, their chemical properties will differ as well. All right. Unlike earlier, the 2 isomers that we discussed earlier, chain and positional isomers, their chemical properties are still the same because the functional group never change. But in functional group isomers, the functional group change, isn't it? So this is carboxylic acid, this is ester. So their chemical properties confirmed are different. Okay. The other set that you learn back in the O level is actually your alcohol and sorry, I'll correct myself. The other side that you learn back in O level is actually your alkene and cycloalkane. Okay, so again, a classical example would be your C4H8 again. Just now you probably remember we did that for butene. And for the case of the cycloalkane, we can also ring it in this manner. This will now be actually our cyclobutane. All right. So again, in the same vein, you will find that between these 2 structures that's drawn, they actually share the same molecular formula. Structures obviously different, but more importantly, their functional groups are different. So chemically, their chemical properties will actually be different as well. All right. Okay. If not, aside from these 2 sets that you learn back in O level, there's another 2 more sets that you need to know for functional group isomers. Okay. Let me continue. So the last 2 sets that you need to know is firstly is actually your alcohol and ether. All right. So alcohol, one example we have is your C3H8O. That's the molecular formula. In terms of line structure for that, we can use a propanol, right? So 1, 2, 3, and then this is actually your OH. So this is actually propane 1-ol. Certainly the oxygen we can shift inside. If the oxygen we shift inside, then this is your CH3, this is CH3CH2. So in this case, this becomes an ether, which means again the functional group of your OH or your alcohol is no longer there. So ether chemically behave very different from your alcohol. All right. The last functional group isomers that we'll be talking about is none other than your aldehyde and ketone. Aldehyde and ketone, again, the formula wise, we can have a C3H6O for molecular formula. So a good example for your aldehyde is 1 to 3 carbon and then a double bond O. I'll just leave it like that. This is actually classically a H. All right. You could actually repeat it. If you don't, it's also fine. Otherwise, the functional group for aldehyde is actually your CHO. Okay. Whereas for your ketone, it's actually your CO, C double bond O. So in the case of ketone, this will be the case. Again, in the same way, chemically, the two of them behave differently. All right. Okay. So that sums up for structural and constitutional isomers. All right. Now we then go to stereoisomers. All right. So as explained, your structural isomers or constitutional isomers, which we just now run through, is your CPF, chain, positional, and functional group isomers, which we just covered. Now we'll be going through stereoisomers. Stereoisomers means they have the same structural formula, same molecular formula, but cannot be superimposed. Right? So that one will be GO. G will be geometric isomers. Then I'll go to optical isomers. Okay, so what is geometric isomers? Geometric isomers typically have a C to C double bond. All right. If you have a C to C double bond, the pi bond, okay, the pi bond between the two carbon restrict the rotation. So a classical example that we always give is none other than your butene. This is an example. So this structure, you can see that if I were to write the structural formula, it's like that. If I were to depict it by line structure, it's like this. However, there's two ways that these molecules could position themselves in the three-dimensional space, and they're not superimposable, all right? Which is this. Okay, in this case, you can see, as I explained earlier, the pi bond prevent the rotation, all right? Restrict the rotation. So it means that if the two carbon rotate, they have to rotate like that together. Therefore, you cannot take this side and just twist and flip it. You cannot flip this side without this side flipping. That means they have to flip together. Okay? If you could twist this side alone, if I can twist this side, then I can, then the structures will become superimposable. All right? So therefore, the first part that you need to understand, in order to, that means for any organic compound that needs that is capable of displaying geometric isomers, they need a C to C double bond. All right? So that's the first criteria. Second criteria, in order that they really display geometric isomerism, the C to C double bond, the carbon atoms involved in the C to C double bond, must have two different groups attached to them. This and this cannot be the same. This and this cannot be the same. Okay, let us give one example. You can see now, if I make this the same. If I make this the same, you realize that this and this straight away become superimposable. Correct? Because they can take and put on top. Are we all right with that? So you need to actually be able to realize that these two cannot be the same, these two cannot be the same. You are comparing these two together and these two together. Okay? All right? So, okay. So in this case, this form a pair of geometric isomers. All right? And this is called geometric isomers, or otherwise we call them cis trunks isomerism. All right? So cis means they're actually on the same side. So the two groupings, again, comparing these two, this actually has a higher MR. All right? Comparing these two, this has a higher MR. So these two, which actually have a higher MR, are actually on the same side. So this is called cis. So this will be labeled as cis butene. Okay? So cis means on the same side. Then as far as this part is concerned, it's trunks. All right? Because they're actually on opposite side. Trunks butene. And also, as explained last week, when you are actually trunks, you are more stable. Why trunks is more stable? You can think about trunks fat. All right. Nowadays, you're very clear when you eat snacks and all that, they always tell you trunks fat is 0. Basically, in a lot of fats that we eat, there's also cis and trunk structure. The natural olive oil contains a lot of cis, which is easily broken down, easily oxidized, good for your body. Your trunks is very stable. All right. It's very stable. It'll be more difficult to break down. All right. So trunks fat is supposed to be bad for you. Bottom line, trunk structure is more stable because they are, the bulky group is on opposite end. So don't have steric hindrance. Unless here, the two bulky group is actually on the same side. They will have steric hindrance, which means that they will have high strain energy. therefore less stable. All right. So if they're less stable, the energy level is higher. If it's more stable, energy level is lower. Okay. So just to quick sidetrack for this, if your energy level is higher or lower, they can link it to a very clear type of questions. If you look at energy level, all right, we can say that if your trunks is actually more stable, yeah. So your trunks should actually be lower. Your Cs be of higher energy level. This is actually your energy level, all right. So in this case, as you can see, if you decide to actually combust the two of them, all right, then you find that in terms of enthalpy of combustion, of course, I won't balance the full equation. This will be CO2 and H2O. Then the enthalpy of combustion for your Cs will actually be more exothermic. Okay. Conversely, you also need to realize that if I were to now do enthalpy of formation, which means to burn them, okay, then you know that your elements will start from here. Everything is 0. So in this case, conversely, you need to realize that your enthalpy of formation is actually more exothermic for the trunks. All happy about it? In summary, you need to remember trunks is actually more stable. Trunks isomer more stable. Cis is less stable. All right. So if it's less stable, energy level is higher. Okay. Now I'll resume. So earlier I covered geometric isomers, saying that basically the same molecular formula, same structural formula cannot superimpose. We talk about the presence of alkene, correct? So for geometric isomers, you have when you have alkene, you need to study it, right? But bear in mind that it means that you need two separate groups bonded to the doubly covalent bonded carbon atoms. Okay, so maybe quick recap again. All right, between these two, it's the two line structures. This one will not be able to display geometric isomerism because this carbon here is bonded to 2H. These 2H are the same. So this one unable to display geometric. This one is able to because CH3 and then an H, correct? CH3 and then one H. So there are two different groups bonded to the two carbon atoms. All right. So therefore, because of that, this structure will represent the Cs, right? The trunks, I'm sorry, because they are on the opposite side. So the Cs will be represented like that. Okay. So this will be trunks. This will be Cs. There will be questions that are asking you about physical properties. All right. So we also want to highlight to you to tell you that actually between the two of them, this is non-polar because alkyl group, as we earlier told you, all alkyl group are electron releasing. Remember this phrase, all alkyl groups are electron releasing. This is actually an A-level marking scheme phrase that you can use extensively in all your organic chemistry. All right. So electron releasing, so they cancel each other. So therefore your trunks butyene is non-polar. This fella is polar because when they release the electron, they did not cancel each other. In a nutshell for this side will be a bit more delta minus, right? This side a bit more delta plus. Okay. So hence, because of that, your non-polar trunks isomer will actually have a lower boiling point. This will actually have a higher boiling point. Okay. Now we're going to tell you another thing which is a bit disturbing, all right? But you need to realize that when it comes to melting point, it's the other way around. I'll now tell you that end up this fella is actually higher boiling point, melting point, I'm sorry. Why? Reason is because it's non-polar. In terms of structures, they can come closer together. Because it's in melting, you actually are bringing the molecules close together. So the ID end up being stronger. In the C structure, because they are polar, when they actually freezes, they have to stack themselves in a certain manner. As probably you can see down here, they're more dispersed, right? Because the delta minus and the delta minus repel. So they cannot come too close, all right? So they're all more spaced out. This one will be more closely, they can be stacked as close as they want together. Hence, because of that, I want you to bear in mind this fella actually have a higher melting point. This one have a lower melting point. So in summary, need to know that the physical properties of geometric isomers are different, right? Similarity, obviously, their chemical properties are still the same. Okay. So I think I covered extensively about how alkene can be geometric isomers. There's another functional group that can also be geometric isomers. They are none other than your cycloalkane. Okay, let us do that. So if you look at the cycloalkane, for example, like these two, all right, and then we look at maybe these structures, C4H6Cl2, all right. So this is actually a 1,2-dichlorocyclobutane, okay, which means that you actually, so in terms of the structural formula, we'll be looking at this, all right. So this is structural formula, but in terms of how the atoms actually position themselves in the three-dimensional space. You remember when we put dotted line, it means actually they go behind the plane. When we put a thick bow line, it comes out of the plane. All right. This one is a thick bow line. It comes out of the plane. This one is a thick bow line. It comes out of the plane. Obviously, there's down at this position here, you all need to realize that there's actually another hydrogen to it, which I didn't draw. Typically, what happens is that you will see that if it's actually a cyclic structure, correct? You will have one atom on top of the plane, one on top below the plane. If the chlorine is actually behind the plane, I have to tell you that technically, it means the hydrogen is on top. Conversely, the hydrogen is below. So it means that for the case of this, the hydrogen obviously is below. Obviously, when you try and superimpose these two, you cannot superimpose them. Why? Because in this case, if this is where the cyclic ring is B, the 2Cl is actually on top, isn't it? On top of the plane. So they are on the same side. So this will be called your cis structure. While in the case of this, you will have one of them behind the plane, one of them in front of the plane. All right. So obviously, this and this cannot be superimposed. And because one is on top, one is below the plane, they are on the opposite side. So therefore, this will be your trans structure. Okay. So hence, in summary, when you analyze or look up for geometric isomers, you definitely gun for anything that has a C to C double bond. And if the C to C double bond, the two carbon that's involved in the C to C bond are attached to two separate groups, two different groups, then they'll be able to display geometric isomers. For the case of this, it is the same rule, all right? This carbon atom must bond to two different types of atoms as well. Similarly, there must be another carbon atoms, adjacent carbon atom that bond to another two different types of atoms. If they are different, then again, you'll be able to display geometric isomers. So for the next group is actually your optical isomers. The word optical already tell you is actually mirror image, all right? So because if it's mirror image, then obviously they cannot be superimposable. Like in the mirror image, if you raise your right hand, actually in the image, the guy is raising his left hand, all right? So obviously it cannot be superimposed. Similar the same vein, if I use the finger, they're mirror image to each other, but obviously they cannot be superimposed because you can see my index finger and my index finger here is on the opposite side. Okay, so the way to depict it or to identify optical isomers, you need something called a chiral carbon. A chiral carbon must be bonded to actually 4 different groups. Okay, so 2 of the groups must sit on the same plane, so it has to be tetrahedral. All right, 2 of the groups sit on the same plane, so maybe it's a CH3. This part could be a CH2 and a CH3. Then you could have one of it that pop out of the plane, which is a Cl, another one which is actually popped behind the plane, which is your H. So this is actually a chiral carbon. So we label that as a chiral carbon. Typically, chiral carbon is represented with actually an asterisk, all right? So you will find that if I do a mirror image of this, they are not superimposable, all right? We'll be able to see it. This and this cannot be superimposed. So in the exam, if people ask you to draw, okay, this one will be a bit fussy. Okay, if they ask you to draw in the exam to display or to draw structural formula to display the 2 optical isomers, then this is the way you depict it. All right, you have to use the thick bow line representing that the atom pop out of the plane and the dotted line that actually pop behind the plane. So this is actually called a pair of optical isomers, and they are actually called enantiomers. Okay, or they are actually called optical isomers, which means same phrase. Huh? Okay, one more thing that we now need to talk about is actually their physical properties. Physical properties and chemical properties 100% the same. The only one, the key difference is that they rotate plane polarized light in the opposite angle. Actually, they rotate them by the same angle, but it's opposite in direction. All right. In the syllabus, you don't have to really know who rotate clockwise and anti-clockwise. Okay. So we're going to make an assumption here. Say, assuming this rotate anti-clockwise, okay, by 5 degrees. Then this will be able to rotate clockwise by 5 degrees. Okay. Which means, in another word, the word to associate or to describe the fact that it can rotate plane polarized light is that we'll say that these structures, all right, these organic compound structures is optically active. Okay, so you're going to pick up another new word to that. So this is optically active. And this alone is also optically active because it can rotate plane polarized light as well. All right. However, if you have a case whereby you have 50% of this and 50% of this, there's a term for it, which is called racemic mixture. Racemic mixture means you have equal amount of each of the enantiomers, 50%, 50%. In that case, racemic mixture becomes optically inactive. Why? Because when the plane polarized light passes through this structure, you rotate it anti-clockwise by 5 degrees. But because there's also a counterpart, the same amount that's present, the same light will then actually be rotated clockwise by 5 degrees, which means the light will come out actually not polarized. The light will come out actually unpolarized. Hence, racemic mixture is optically inactive. All right. Those who are happy, give me a thumbs up. Remember, when you're looking for optical isomers, you're going after a chiral carbon, which in other words, it means that the chiral carbon must be bonded to 4 separate groups. The last but not least is that we give you one couple of examples on optical isomers. All right, a very classical one that I love to talk about is actually this one, and I like to talk about it using I always like to talk about this one. Okay, so a very quick one as far as this fellow is concerned, he has 0 chiral carbon. All right, this one also have 0 chiral carbon. Some people will counter argue to say that why not this be chiral carbon? All right. After all, this one pop out of the plane. This is a H. It looks like they have different groups here, but actually it's still symmetrical because imagine if you have the carbon standing there, you will find that here and here is still symmetrical. All right. In the same vein, this is actually the same as well. Here and here is actually the same as well. Okay. So therefore, for both these structures, they have 0 chiral carbon. If you want to make sure they have a chiral carbon, the way to alter it is this. And all it does is for me to shift it this way. This means that these 2 carbons become chiral. They become chiral because you realize that if the carbon, you personify it and you stand down there, then obviously looking from this and this, it cannot be symmetrical. All right. And this is obviously, it has 4 different groups. Similarly, in the same vein, when they look at it from this and this perspective, all right, and you also have 4 different groups, so you will end up with 2 chiral carbon.